Hello, bachcho. Welcome to class. So today we're going to tackle a really important topic from our unit on electromagnetic induction, and that is magnetic flux. Now, don't get worried by the name, okay? This idea is actually the key to understanding this entire chapter, and I promise you, we will make it so simple and so exam safe that it becomes crystal clear. Alright, chalo, let's start with a little bit of a surprising question. Just imagine, okay? You have a magnet, and right next to it, there's a wire, a loop of wire. Both are just sitting there, perfectly still, no movement whatsoever. Now my question is, can you still generate electricity in that wire? What do you think? The answer is yes, you actually can. Now you must be thinking, how is that possible, sir? Well, we'll get there, but this little puzzle, this is the whole point of what we are going to learn today.
So, to solve that puzzle, first we need to get our heads around a new concept, a new quantity called magnetic flux. But wait, before we open the textbook and look at all the scary definitions and formulas, let's try to understand the main idea, the core idea, with a very simple example from our daily life. Okay, everyone, just picture this in your mind. It's raining outside, and you're just looking at the rain falling through an open window in your room. That's all. Got that picture? Good, because this simple scene is all you'll need to understand magnetic flux. Seriously. So look here. Think of the magnetic field lines as, well, as these raindrops. And the area of your wire loop, that's your window. So what is magnetic flux then? It's nothing more than counting how much magnetic field is passing through a certain area. Simple, no? I mean, if it's raining very heavily, or if your window is very big, obviously more water is going to come in, right? It's exactly the same here. If the magnetic field is strong, or if the area of your loop is large, the magnetic flux will be high.
All right, so this rain and window idea, it gives you the feel of the concept, right? It makes sense. But in the exam, you need the proper words to get full marks, isn't it? So now, let's look at the official definition, the one that's directly from your NCERT textbook.
Okay, this is it. This is the definition you have to learn by heart. Magnetic flux through a plane of area A, placed in a uniform magnetic field B, is given by phi B equals B dot A, which equals BA cos theta. The most important part here is that formula. Flux, which we write with this Greek letter phi. Phi is equal to B multiplied by A multiplied by cos theta. Now, let's break down this formula using our same rain analogy so you never forget it. Okay? First, B. B is the magnetic field strength. So that's just like asking, how heavily is it raining? Simple. Next, A. A is the area of the loop. That's like asking, how big is your window? Easy. And finally, the most crucial part, cos theta. This is all about the angle, the orientation. It basically tells us how tilted your window is with respect to the rain. And this picture here, it makes the role of this angle perfectly clear. Look on the left. The window is completely flat, facing the rain head-on. Rain is falling straight down, so maximum raindrops will pass through, right? Here, the angle theta is 0 degrees, and what is cos of 0? It's 1, so we get maximum flux. Now, look at the right side. The window is standing up, vertical. It's parallel to the rain. Tell me, will any single raindrop enter? Of course not. Here, the angle theta is 90 degrees, and cos of 90 is 0, so the flux is 0. And please remember this. Theta is the angle between the magnetic field and the normal to the area, not the surface of the area itself. Very important point. So now we know what flux is. Great, but listen carefully. For generating electricity, which is our main goal, right? The amount of flux itself is not that important. What's important, what's absolutely crucial, is the change in flux. So the question is, how can we change it? Well, it's actually quite simple. There are 3 levers you can pull, and they're all hiding right there in the formula. It all comes from the formula phi equals BA cos theta. If you want to change phi, you just have to change one of its parts. Simple. So first, you can change the magnetic field strength, B. This is like making the rain fall heavier or lighter. Second, you can change the area of the loop, A. That's like making your window bigger or smaller to catch more or less rain. And third, you can change the orientation or the angle, theta. That's just like tilting your window. You do any of these 3 things, you will change the number of raindrops getting through, and that means you have changed the magnetic flux. Okay, that's enough theory for now. Let's solve one very small numerical problem. This will make the formula feel real, and it will give you some good confidence for your exams. So here is the data for our problem. We have a magnetic field B of 0.5 Tesla.
The area of the loop, A, is 0.02 square meters. And listen to this part carefully. The field is perpendicular to the loop. That means it is parallel to the normal of the loop. So what is our angle theta? It's 0 degrees. Okay?
Now we just have to apply the formula we learned. Phi equals B into A into cos theta. So let's put in the values. 0.5 for B, 0.02 for A, and cos of 0 degrees. And cos 0 is just 1. So we multiply them, and what do we get? 0.01. And what's the unit? The unit of magnetic flux is the Weber, which we write as WB. See? So simple.
Okay, now for a very, very important point. Everyone, please pay full attention. I want to talk about a silent killer in exams, a common mistake that so many students make, and it costs them very precious marks.
So the wrong idea, the thing many students believe, is that if you take a wire loop and put it in a very strong magnetic field, you'll get a current. This is completely 100% wrong. The correct idea, the one you need to remember, is that only a changing magnetic flux can produce a current. I'll say it again. It doesn't matter how strong the field is, if it's constant and the loop is just sitting there, the flux is not changing, and you will get zero current. Nothing.
So, the most crucial takeaway is this golden rule. I want you to lock this sentence in your brain. Just repeat it with me. No change in flux, no current in the circuit. That's it. If you remember this one simple line, you will never, ever make this mistake in your exam.
Now, I know some of you might be wondering, Sir, why are we spending so much time on just one single idea of flux? And the reason is very simple, Beta. This concept, it is the foundation stone for this entire chapter. It's the base of the pyramid.
You see, if you have truly understood what magnetic flux is and, more importantly, how to change it, then congratulations. You have just unlocked the secret to understanding Faraday's law of induction, Lenz's law, and you know what else? Even how those massive AC generators that give electricity to our cities, how they actually work. Everything. It all starts with flux. So before we finish, let's do a super quick summary, okay? Point number 1, magnetic flux, phi, is just a count of how much magnetic field is passing through an area. Point 2, the formula is simple. Phi equals B A cos theta. Point 3, we can change this flux by changing B, A, or theta. And the most important point, number 4, only a change in flux will induce an EMF or a current.
Okay, so we've agreed that changing the flux creates a voltage, or an EMF. But here is my final question to you. What is the exact connection? I mean, how does the rate of change, the speed at which the flux is changing, how does that relate to how much voltage you get? Is there a mathematical rule? Is there a formula for it? Think about that, because that is the exact question we are going to answer in our very next explainer on Faraday's law. I'll see you then.